So we have our schedule for the rest of the semester. We're going to finish up 6-4 today and do 6-5. Those are fairly easy. Then we're going to do 7-4, which I think is one of the best and most fun topics that you'll use a lot in Calc 1. Also 7-3, not as fun, a little bit more difficult, but again used a lot in Calc 1. Monday I'll teach 7-1 and 7-2. It's not an easy lecture. Make sure you take your Advil before you come to class. It'll be a shorter class because of Thanksgiving. So I'm hoping to stay for an hour, okay? When we come back from Thanksgiving, we'll finish chapter 7. Then we're going to review, and then we'll take our test 3. Then again, then we'll review, and then we'll take our our final exam on Monday. I believe it's 12/12. So it's December 12th. Let me just double check that. And we're meeting at, it's a weird time, I remember that too. Yes, December 12th. And the time is strange. Let's see, the first exam goes from 8 to 10. Next exam goes from 10:30 to 12:30. Next exam goes from 1 to 3. That's us. 1 to 3. I'm pretty sure. Let me just double check. So if you go to the main website, Montgomery College, and I do final exam schedule. Yeah, fall 2022. We meet Monday and Wednesday, so I'm looking at this column. We start at 2 o'clock, so between 1:55 and 2:54. So I'm looking at this row. All right, so I was wrong. So we start at 2:45. We start late. Do you see that intersection there? So I'm looking at this column. It won't let me click on the column. So I'm looking at this column and this row, and the intersection says December 12th, 2:45. So that's okay because if you're here to class on time, you won't be late. That's for sure. If you're here for class at 2, you just have to wait. I mean, maybe I'll let you start at 2:30. I think the room will be open. I'm not guaranteeing that. So 2:45 to 4:45. I'll try and remind you every day, every class until the end, okay? Any questions about the schedule? You need the final, right? If you pass the final, you pass the class. I'm also going to take the final exam grade and replace a lower test grade. So if your test 2 was a 20 and you get a 60 on the final, I'll replace your test 2 with a 60, right? As long as it's higher than your lowest test grade, I'll replace it. So there's a couple of safety nets there. What I'm worried about is that if you squeak by with a 70 in the class, you're missing a lot of the material. How well are you really going to do in Calc 1, right? That's what I'm worried about. My job is to prepare you for Calc 1, but I can't deny you passing the class if you earn a 70, right? But will you really be ready for Calc 1 in that case? And I'll say to you this, the trig stuff is what I see as the weakest part of my calculus students. So you really want to know this chapter 6 and 7 as you're going into calculus, okay? You want to get into that calculus class as soon as you can as well, unless you're not taking Calc 1, right? If you're not taking Calc 1, don't worry about it. So, but otherwise, you want to register now. Don't wait. Get into a section that's good for you. You don't have to take it with me. You can take it with anyone. I'm preparing you to take Calc 1 with any teacher on campus. I'm preparing you to take Calc 1 at UMD, right? I don't know if I'm preparing you to take Calc 1 at MIT or Stanford, but Princeton, maybe not. It's close. Good. So let's take a look at 6.3 again. I am recording, and I did post Monday's recording also. Okay. On Blackboard, I posted it. So 6.3, we're talking about the graphs of sine and cosine. And the only thing we're adding today to what we did on Monday is we're adding frequency modulation. So we're going to add frequency modulation today. So, for example, we want to know the mother function for sine and cosine. Okay, we want to have it memorized on our formula sheet, anything like that. Of course, you can always graph it on Desmos, so take advantage of that, right, if you forget things. But for y equals sine of x, what I want to have is I want to have my quarter steps set, okay? My quarter steps are quarter around a circle every time. So the whole circle is 2 pi, so quarter step, right? So my quarter steps would be 2 pi over 4 quarters, of course, right? Which is pi over 2. So this one is 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. I don't usually reduce them because I just want to be kind of robotic about it as quarter steps. The first quarter step, the second quarter step, third quarter step. I want to be thinking of the sine happening left of the origin and right of the origin, but the mother function we'll be talking about is always right of the origin. So I remember that sine starts at 0, climbs to 1, comes back to 0, climbs down to -1, and goes back to 0. So there's my sine function. And of course, it is repeating. So meaning it's over here as well. Right? You see, I'm kind of ghosting that left-hand version of it, but I'm really looking at quadrants 1, 2, 3, and 4 here. Do you see those quadrants? Right? You see those quadrants there? And what I'm really trying to focus on is this box. Right? That box is what I want to really see. Kind of like my 1 by 1 box for all my mother functions. Only this one is 2 by 2 pi, right? The height is 2, and the width is 2 pi. So I'm going to ask you on the chapter, the test 3, and on the final, to graph me the mother function and a daughter function. And the daughter function will either be an amplitude modulation or a frequency modulation. So let's do one real quick with an amplitude modulation. So we want to graph. So this is a amp modulation, AM radio. So I want to graph y equals -2 sine of x. So I'm changing that lead coefficient. I'm changing the radius of the circle, right? It used to be a radius of 1. Now it's a radius of 2, but I'm saying reflected on the x-axis, right? If I say negative, it means all of the positive numbers are now negative numbers, and all the negative numbers are now positive numbers. When I do this, I want to graph the mother. So I'm going to graph the sine function with my quarter steps at a height of 1, max height of 1, min height of -1. And then on that, I'm going to superimpose the daughter, okay? So we already have this sine function here, right? And of course, how am I remembering that it starts at 0? I'm just looking at my chart, right? My reference chart. Square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, right? Everybody with me there on that? So there's my mother. There's y equals sine of x. And on top of it, I want to superimpose the amplitude modulation. So that means I'm going now up to 2, down to -2, and all my quarter steps are the same. So you can see my new box, right? You can see the old box, right? There's the old box. 2 units high, 2 pi units wide, right? So, but my new box now is 2 high, +2 up, and then -2 down, so has a height of 4, and still the same width, right? Now, but where am I starting? So I want to graph y equals, I want to graph this one, right? So where am I starting? I'm starting at 0 again. But instead of going up, I'm going to start down, right? Then back to 0, then to +2, and then all the way back to 0 again. So you can see the mother function and the daughter function all in the same grid. Is that making sense at all? Watch me on Desmos. Yeah, question? Question? It does. So that negative says flipped it upside, exactly. Make all the positive negatives, all the negatives positive, right? So on Desmos, I wanna see the same thing. And I like to restrict my domain so I can just really focus on that one particular function. That one particular piece of the function, right? So I'm going to start with the mother function, y equals, so y equals sine of x. And I'm going to restrict my domain, curly bracket 0 is less than x, which is less than 2 pi. So I'm restricting it to that one piece of that mother function, right? Then I want to put in my amplitude modulation. So I had y equals -2 times the sine of x. And you can see the, right? And again, I would like to restrict it, right? Curly bracket 0 less than x less than 2 pi. And you'll see when I'm solving equations today, which is 7.3, which is the last half of this packet I printed for you, I'll draw the trig functions quickly all the time with the purpose of, and you'll see it, knowing which quadrants my answers are in, okay? So there's our amplitude modulation. Let's do frequency modulation now, right? Everybody comfortable here? So it's like, well, you know, how difficult of a problem is this if you can use Desmos anyway, right? It's not at all. The difficult problems come in 6.6, and I'm thinking about skipping them because I'm like, you know, yes, I had to go through the pain of learning it, but do you really need it for calculus? Is what I'm trying to, you know, sift through. I'm trying to filter things out that are kind of painful now that I don't really need in calculus, especially if you're doing things computer-based. All right, so let's do a frequency modulation now. So I'm gonna alter this multiplier inside of the sine function. So B is called my frequency. And if B is larger than 1, it's more frequent. If it's less than 1, it's less frequent, right? Meaning you're going to see the graph repeated more or less. So, and the key here is that the new period is going to be 2 pi over B. And of course, the new quarter steps will be 2 pi over B divided by 4. Right? So you'll see that come into play. And again, the quarter steps, what I'm thinking about is where are the quadrants of our grid, right? Where is quadrant 1? Where is quadrant 2? Where is quadrant 3? Where is quadrant 4 in terms of the graph? That's what I want to be thinking about. So let's do a quick, easy one. So we're going to graph y equals sine of 2x. So doubled the frequency. So I double the graph. Okay? I want to be able to look at the original function, y equals sine x. I got my quarter steps. I know my height is 1, my depth is minus 1. And I know what my sine function looks like. Starts at 0, goes to 1, back to 0, down to negative 1, back to 0. So there's the mother function, y equals sine x. My quarter steps in that case are the usual ones, right? Pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, all the way around a circle, right? So, but in this case, in my new piece, B is 2, so 2 pi divided by 2 says that the period is now pi. So meaning the sine function is going to end at pi. You're going to see it happen from 0 to pi instead of 0 to 2 pi. Right? Is that making sense? Right? So, but I want to think of my new quarter steps, right? Which of course are pi over 4s, because I'm going to take the period divided by 4. So I need a pi over 4. So I really need, I'm going to have 8 tick marks now. Because I want sine to start at 0, go to 1, back to 0, down to negative 1, back to 0. So there's sine of 2x. And what I want you to do is graph it on top of the mother function. So meaning, keep going with it. 0 to 1 to 0 to negative 1 to 0. So what you can see is the sine function happening twice, because the frequency is 2, when the mother function had a frequency of 1, so you only see that wave once. So if we do that on Desmos, right, we got our mother function. We're going to put sine of 2x in here. And again, so you can see the sine function happening twice, that wave happening twice. Yes, you with me? And this is the same exact wave of striking a string on an instrument. If you could put a strobe light on a string while it's vibrating, you'll see it making this exact same thing, a sound wave, a string wave, right? So when I look at this, I hear a low E and an octave. So when I hit the low open E string on my guitar, you can hear the note, right? There's 1 point moving around the circle. And then when I hit the 12th fret, an octave higher, I cut the string in half. That 2 is twice as fast. So now the other point is moving twice as fast around the circle. right? And then so I'm hearing the two notes here. I hear a note and its octave. So that's it for 6/3. Let's talk about 6/4. So we want to graph tangent and the other trigs. So tangent, cotangent, secant, cosecant, right? I typically don't bother too much with cotangent, but we should definitely know the tangent curve. So the tangent curve has a period of pi So there's the mother function for the tangent curve. And you say to me, well, what's going on here, right? So I really want you to be seeing quadrant 1 here, and then what quadrants on the other side? Well, what's the quadrant on the left side there? Is it 2? It's either 2 or 4. It's 4. Because I count 1, 2, 3, 4, 1, 2, 3, 4, or 4, 3, 2, 1, 4, 3, 2, 1, 4, 3, right? So I want to be thinking of my circle, my radius, my right triangle, and remember tangent is the slope of the hypotenuse, right? So right there, I'm talking about that point right there, a positive slope, right? If I did this triangle down here, right, we're talking about somewhere around here, a negative slope. So if we think about starting in quadrant 4 with this triangle, right? We're starting in quadrant 4 with this triangle. Negative slope, right? Negative slope, almost 0, right? Then positive slope, positive slope, positive slope, right? And then it repeats, right? Once I get into quadrant 2, I've got a negative slope again. Right? So tangent is undefined. At odd pi over 2's. So meaning negative 3 pi over 2, negative 1 pi over 2, 1 pi over 2, 3 pi over 2, dot, 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 each way. And a nice way to say odd pi over 2's is 2n minus 1 pi over 2's. So kind of a nice thing to do with the tangent curve on Desmos is just graph the tangent curve for me. And we're trying to focus in on the mother function. Nice to kind of change my gearbox to pi over 2's. Right, because you can really see those vertical asymptotes there, right? And then it's kind of nice to graph a couple of points from my reference table. So if I pick pi over 6, what's the tangent value there? So rad 3 over 3. So it's kind of nice to graph that square root of 3, square root of 3 over 3, just so I can see it on the curve there. Yeah, okay.
With the table of values for sine, cosine, what just have to remember that?
Yeah, but it's so easy. It's so easy. It's so 0 pi over 6. Come on, Robert. Pi over 4, pi over 3, pi over 2. I can't, nothing's working for me today. Pi over 3, pi over 2, square root of 0 over 2, square root of 1 over 2, square root of 2 over 2, square root of 3 over 2, square root of 4 over 2. Cosine just works the other way. Tangent is sine divided by cosine. But you have a formula sheet, so put it on the formula sheet. But yes, you should memorize it. It's easy. Yeah, it's easy, right? Nice. So there's our tangent curve. I don't typically ask too much with the tangent curve. If you looked at applications of the tangent curve, it doesn't do much. So if I said 5 times the tangent curve, it just stretches it up more, right? And then if I did frequencies, so tangent of 2x, it's just going to change my period. Instead of having a period of pi, it's now got a period of pi over 2. So, but I don't usually typically do too much with tangent curves. Again, if I have a problem with a tangent curve, a tangent function, I will draw the tangent curve, okay? And you'll see what I mean when I do problems in 7.3. All right, last thing to do in 6.5 is to graph a secant curve or a cosecant curve. The process is the same, so let me just do one of them, and then you try the other, right? So let's look at graphing a secant curve. Well, this is related to cosine, right? So when someone asks you to graph a secant curve, I want you to graph a cosine curve. Okay, so cosine curve. Quadrants. Cosine starts at 1 and then goes down to 0, down to -1, back to 0, back to +1. I like to think of the cosine curve as a smile. It's an easy way for me to think of what the cosine is. And I kind of want to extend it a little bit. I want to extend it past the mother, right? So starts at 1, down to, right? So etc. And then, of course, over here. So there's my cosine curve, just a little bit extended. A couple of quadrants further right and a couple of quadrants further left. And I want to remember that the secant is 1 over the cos. So when cosine is 0, secant is in trouble, right? You agree? When cosine is 0, secant is undefined. You with me there? When cosine is 0, I'm dividing by 0. So every time I get a cosine of 0, I'm drawing a vertical asymptote. Every time I get a cosine of 0, I'm drawing a vertical asymptote there for my secant curve. And the secant curve is just the upside down of the cosine curve. So it's there, it's here, it's here, right? That's the secant curve. So there's my secant curve. It's that simple. And think about it. What is y equals cosine of 0? We know that's 1. And what is y equals secant of 0? Right? Well, that's 1 over cos of 0. So that's still 1. Right? So at 0, those two graphs are hitting each other. What's y equals cosine of pi over 3? Hello? What's cosine of pi over 3? 1/2, thank you. So what's y equals secant of pi over 3? It's a reciprocal, so 2. So a secant curve or a cosecant curve are very simple, right? And let's look on Desmos. So first we want to graph the cosine of x. I'd like to put in vertical asymptotes anywhere cosine is 0. So meaning I want to put in where's first time cosine is 0 is pi over 2. So I'll put in the line x equals pi over 2. Right? And I'll dash it. Because it's a vertical asymptote, right? So I've got another one, minus pi over 2. Remember I said, no, I didn't say anything there. So minus pi over 2. And again, I want to dash it just to show that it's a vertical asymptote. So I just picked those first two closest zeros to the origin just because I'm lazy. I don't want to do them all. And then I want to graph my secant curve, y equals secant of x. And you can see it's filling in its reciprocals, right? Right? Is that making sense? So right here is reciprocal of 1 is also 1. It's on the secant curve. Right here is a 1/2. Reciprocal of 1/2 is a 2. There's a 2, a height of 2 on that secant curve, right? And when cosine goes to 0, the reciprocal of 0 is undefined, infinitely steep, right? So looking at the textbook, looking at the textbook for 6.3, 6.4, 6.5, right now my plan is to skip 6.6 because it's so horrible and it's not that needed in Calc 1. Not needed at all, actually. Any day, book. Johannes, I don't know why I didn't give this back to you Monday. I just probably lost my mind a little bit. Just waiting for the book to load.
Yes, so remember, three players, the one player, two players, three players, sign is the height. So what height is that? There's one, right? So you're only thinking about. So C is reciprocal negative. Right, the sign is -1. So C is reciprocal of sign. So it's reciprocal -1, -1.
Right, 1 over -1. How about that, right? Oh, here's a book. So in 6.4, I would like you to do nice, thank you. Oh, you don't have to give me that. You can keep it. Yeah, I'm just saying you should do it.
Oh, it's
You don't have to. Yeah, you don't have to turn it in now. I don't know, 41. Do 41. So they're giving you an amplitude and a frequency modulation, right? They're giving you an amplitude and a frequency modulation. I don't know, 27. And 41. Do those two, okay? In 6.5, I don't know, 25. 25, 31. Okay? What did I say in 6.4? 27 and 31? 41? '25 and 31 and 6.5. In 6.4, I like, I'm just writing it down to make sure. Yeah, 27 and 41. Nice, thank you. Cool, here comes the fun stuff. We'll take a break in a little bit, okay? So we're looking at section 7.3 now. So 7.1 and 7.2 are inverse trig functions. So we have to talk about that. We're going to do that Monday. But today we're going to start with section 7.4 because it's fun. At least it is for this nerd. So 7.4 is called establishing trig identities or proving trig identities. And we need a whole slew we need all our trig identities to prove trig identities. And so we have several, right? What do we have? We have tangent of theta is sine of theta over cos of theta, right? We have sine squared theta plus cos squared theta equals 1. And the other 8 from that, which I talked about Monday, right? All the Pythagorean identities. We need our odd and even identities. So these are just the simple identities. These are the Pythagoreans. Odd and even, right? Sine of theta is the same as the opposite of sine of the opposite of theta. Et cetera, et cetera. We need them all, right? So you have them all on your formula sheet, right? I'm not writing them all down because you have them, right? So, and we're going to start to add more identities Monday. But right now, this is just my first list. Do you remember the Pythagorean? Can you see, if I gave you this one, can you see another one real quick? Sine squared theta equals what? 1 minus cos squared theta, yeah. Right? Remember I had 9 of them? Okay, here we go. Proving trig identities, kind of a step-by-step, okay? The first idea is to change everything to sines and cosines. When you get good, you won't have to do that. But when you're first learning, it's the easiest to do this. I want to start on the more difficult side. And again, once you're good, you should be able to start on both sides, either side. And I want to and never cross sides. So we learned a long time ago, you can add 2 to both sides and you keep it equal. Or you could divide both sides by 5 and keep it equal. We are never crossing a side. We're going to pretend there's only one side. And the idea is work on one side until you get it to look exactly like the other side. If you get stuck on one side, go to the other side and work on that side. And then eventually they'll match up, you're done. You're going to do some tricks like LCDs. You might have to factor. You might have to use a conjugate. You might have to use a trig identity like a Pythagorean. So these are the things that you might have to do. I think that's it, but I'll put etc. in case I stumble upon another one. So once again, I want to start on one side, work on that, pretend the other side doesn't exist until I match the other side. If I get stuck, I don't know what to do, I can then switch sides and start working on the other one until I get something to match, right? And then in that case, we say you've proven the identity. As soon as you get the 2 sides to match, you've proven the identity. Let's start right away with something nice and simple here. We might as well do 21. So this is 7.4, number 21. The first 2 pages I gave you today are 7.4. okay? First 2 pages I gave you were 7.4. The second 2 pages are 7.3. Why am I doing that one later? Because it's difficult. 7.4 is easy, okay? So it's nice to have some easy problems to work on. So what do I have on the left? Cosecant theta? Cosecant theta times cosine of theta equals cotan of theta. Now, if you are bad at factoring, if you are bad at fractions, if you are bad at solve for x, this stuff is going to be a nightmare, but you have to be able to do it. So let's get over this fraction nonsense. There's no reason to not be able to do fractions, please. Let's get over this factoring thing. If you need to go back and review your factoring from Algebra 2, from Algebra 1, do it. If you skip Math 50, if you test it into pre-cal, meaning you skip Math 50, and you skip trig, then you skipped all of the practice you need to be able to do this. So if you can't do it, you can't avoid it. You have to get in there and get dirty. You have to be able to do fractions. You have to be able to factor. Well, this one is a real simple one. I'm just going to change everything into sines and cosines. So I have a cosine over a sine, and that should equal a cotangent. And I'm done, aren't I? Change everything to cosines and sines. What's on the, so left-hand side, I have cosine over sine. You should know that's already cotangent. But you can change the cotangent too. What's cotangent? Oh, guess what? Cosine over sine. Done. Done. As soon as I get them to match, I'm finished. Don't worry, they're all not that easy, right? And there'll be a couple that you just won't be able to do for some reason. Let it go. Try it again later. Try it again the next day. Let your brain defrag. I don't know if you know what I mean by, you remember when computers had to do a defrag late at night? You remember this time? And you'd see all these puzzle pieces kind of floating on the screen. What they're doing is when you're working on your computer, so you go do an email, and then you work on a Word doc, and then you download a song. All of that stuff is being just kind of layered into memory as you do them. And then the computer says, okay, when the owner goes to sleep, I'll take all of the pieces of Word that are stacked all over and put them together. So I take the fragments of memory that belong together and put them together. It's the same thing we need as humans. If you're trying something, you're stuck on it, and you just keep, I'm stuck, I can't get it. Let it go, and then try it later, and things will work out, okay? Let's do another one. Let's do 39. And you'll see what I'm going to do here. So I've got secant of u minus tangent of u. Who cares what the letter is, right? As long as they're all the same, equals cos of u over 1 plus sine of u. So I'm going to change the sines and cosines, and I'm going to cheat a little bit. What do you think is the more complicated side? What do you think is the more complicated side here? I would say maybe the right side, but I'm going to start on the left side because I want to change things to sine and cosine. So I have 1 over cosine minus sine over cosine. So, and you can see how lazy I am. I don't want to write out sine of theta, sine of u. I just want to write s. Yes, you with me? So I don't know if you see it, but don't I have fractions with the same base? Right? So I really have 1 minus sine over cosine here. I'm stuck. I don't know what to do, but I know on the other side I have cosine over 1 plus sine. And so when I see 1 plus or minus a trig, I want to think conjugate. When you see 1 plus or minus a trig, think conjugate. So I'm going to work on the left because I feel like it. And I want to say 1 minus sine over c, and I'm going to multiply by 1 in the conjugate over, in the form of the conjugate over itself. So 1 plus s over 1 plus s. Again, I'm only working on one side. What do I get when I multiply in the numerator? What do you get when you multiply and get with conjugates? What do you get? I'm foiling, yes? Yes? What do I get? 1 minus. So it's 1 minus sine. There you go, 1 minus sine squared. Right? The conjugate, the middle terms drop out. Yes? Does anyone need to see that? What is 1 minus sine squared? When you see 1 minus a trig squared, you are thinking Pythagorean. So what is 1 minus sine squared? Yep, cos squared. And now one of my cosines cancel, right? So I get c over 1 plus s, done. Yes. Yeah. I'm very lazy. I don't feel like writing all that crap out every time. But you got to be careful, right? You got to make sure you don't call a cosecant a c, right? You got to be careful of that. First, turn everything to sines and cosines, and then take that shortcut. Not too bad, right? So there's lots of little subtle tricks that you just have to get in there and do until you figure everything out. Let's do 59. Is this okay? Yep, I'll wait. Yep, I'm in no hurry. Yes, where do you want? Yep, good. I usually put 3 of these on the next test. One where you'll have to use a conjugate, one where you'll have to get an LCD, one where you'll have to factor. Let's do 59. Is that okay? We ready? Yep. So I've got the tangent of theta plus cos of theta over 1 plus sine of theta. I might need a conjugate there, equals secant of theta. Clearly the left-hand side is more difficult, but I'm going to change them all to sines and cosines anyway, right away. So I've got a sine over cosine for tangent plus cosine over 1 plus sine equals 1 over cosine. Right? Secant is reciprocal of cosine. Is everybody comfortable there? I want to focus on the left-hand side. I see I'm adding 2 fractions. In general, when I'm adding 2 fractions, I want an LCD. So what's my LCD here on the left side? Well, you just look at the denominators and multiply them together. So c times 1 plus c. So in this one, I need a 1 plus s. Let me make it green, sorry. On this one, I need a 1 plus s over itself. And on this one, I need a c over c. And again, I'm working on the left-hand side. And I'm getting an LCD, yes? Good. What do I have now on my left-hand side? In the denominator, I just have c times 1 plus s. In the numerator, I have s times 1 plus s plus c squared. And so I'm thinking I got to do a little bit more work there. So I'm going to distribute, right? I don't know what else to do. What do I get? Sine plus sine squared plus cos squared equals c times 1 plus s. I'm sorry, divided by c times 1 plus s. Everybody following me? Do something. Do something. Get an LCD. Try a conjugate. Try to factor. Try to distribute. Go ahead. Look at that. It falls apart, doesn't it? I've got sine plus 1 now upstairs, and that's going to cancel with the 1 plus sine downstairs, right? And I'm done. I get 1 over c. I'm done. That's what I wanted. Easy. But you got to be patient. You got to be able to do LCDs. You got to be able to factor. You got to be able to do trig subs, right? Using the identities. Yeah, where are you? So my first line there is where I changed to sines and cosines. I decided to work on the left side, and I got an LCD. Then I just simplified, found a trig identity, something canceled, and I was done. In calculus, what's going to happen is you're going to have these very, very complicated trig functions that if you do the process we're doing now, those functions become very simple. And that's what we want. We want to work with simple machines. Let's do another. How about 82? So by the way, you don't have to do odds only here because you're going to know if you have it right, they're going to match, right? Left side will match right side. So you can do anything. So 82. I've got sine plus cosine over sine. Oops. Minus cosine minus sine over cosine equals 1 over sine times cosine, right? Secant is 1 over cosine. Cosecant is 1 over sine. So the sine and cosine are in the denominator. Clearly, the left-hand side is more complicated. What's my LCD? Yeah, sine, cosine. So I need to multiply this one by cosine over cosine and this one by sine over sine. Kind of nice already because I see my downstairs is exactly what I want on the right side, right? So I have s plus c times c minus c minus s times s. So I just rewrote my numerator, but I'm going to distribute, of course. Oh, it's done. It's easy. Sine times cosine cancels, and then cos squared plus sine squared is 1, right? Done. It's too easy. Get good at it. Do all of them. Okay? Get good at this. Do all of them. Nice. Let's take a little break. Come back at 3:10.